Sorry. So in this talk, thank you first of all for the invitation. And in this talk, I will present the results I obtained recently, collaborating with people in Gran Sasso Science Institute and in collaboration with Observatorio Astronomico di Brera. And I will talk about the origin of stiff decay in gamma ray bursts. So first of all, let me give you a brief introduction about gamma ray bursts. They are cataclysmatic events occurring at cosmological distances, extremely energetic, and they are formed by two channels of formation. One is the collapse of a massive star, the other is the coalescence of two compact objects. And in both cases, we have the formation of an accretion disk, which triggers the launch of a relatively collimated jet. And this jet is able to dissipate its internal energy under the form of gamma rays. And this is also known as the prompt emission phase, which is highly variable and erratic. Then, in the following phase, we have the interaction of the jet with the interstellar medium. So while the jet is decelerating, we have the so-called afterglow phase, which can be seen from radio to very high energy gamma rays. Now, one of the most puzzling points of the gamma ray physics is the origin of prompt emission. And so we have to understand what is the nature of this emission, what is the physical process behind it. And recent studies have demonstrated that this emission is compatible with a synchrotron emission. The problem is that the same studies demonstrated that these particles responsible for emission are not able to cool efficiently. And this is a controversial problem because we expect for gamma ray bursts to have compact, highly magnetized environment. So we expect that the timescales, the cooling timescales of particles are extremely small. So in order to further investigate this problem, we tried to study a specific phase in the X-ray light curve of gamma ray burst, which is known as the stiff decay phase. So you can imagine that if the prompt emission is like a fire, so highly variable and highly energetic, the stiff decay, which is the tail of the prompt emission, is like the light coming from the coals left after the fire. So analyzing the behavior of the drop in flux and the spectral evolution in this specific case, we are able to shed light on the cooling of particles once the acceleration mechanism takes over. So for this purpose, the use of the Swift Observatory was fundamental. Indeed, past studies demonstrated that during the stiff decay observed in the XRT band, which is between 0.2 and 10 keV, it's possible to see a systematic softening of the spectrum, which you can see in the bottom panels here, where you have the photon index, which is always increasing in time while the flux is going down. And this is usually interpreted as a gradual shift of the characteristic frequency of the intrinsic spectrum in the observer frame. So we tried to do a similar work analyzing the archival data of the Swift database. And what we did is a systematic time-resolved spectral analysis of XRT light curves. So what we did, for each time being of the light curve, we extracted the spectrum and we fitted with an absorbed power law, and we analyzed the evolution of the photon index alpha as a function of time, with a specific concentration of our focus on the steep decay phase. And this is what we found for two specific samples. The first one that you see on the bottom part of the slide is a sample which has of gamma ray bursts that have in the XRT light curve a clear indication of steep decay, which has a power law behavior in time, with a well-defined peak time, and corresponding in correspondence we have a very bright emission in hard X-rays. And if we study the spectral evolution during this steep decay, this is the result in these plots. This is the photon index as a function of the inverse of the normalized flux. And you see that there is a tight and quite universal correlation between these two observables for all the elements of our samples. And also this is confirmed if we extend the sample, trying to include also those cases for which the steep decay doesn't have a well-defined peak, but we are able to extract the maximum flux, extrapolating back up to the peak time of the hard X-ray peak. So since this relation seems to be quite universal, we thought that it's necessary to search for a universal process that is shaping this spectral evolution. So we need for this a process that gives a steep drop in flux and at the same time a softening of the spectrum in the soft X-rays. Now the softening can be given or by an intrinsic evolution of the spectral shape, or by an overall redshift of the spectrum with an intrinsic constant shape. And in particular, we focused on this second possibility, which is represented in this sketch, in this sketch on the bottom part. So you see that if you have a spectrum in the observer frame which is curved, and this spectrum is crossing the observing band, in this case the XRT band, you see that if also the peak flux is going down with time, we see in the XRT band a flux that is decreasing, and at the same time a photon index that is increasing, so a softening of the spectrum. Now, in order to model this process carefully, we studied two opposite regimes. One is the radiative regime and the other is the adiabatic regime. In the radiative regime, we are assuming that the cooling timescale due to radiative losses are much smaller than dynamic timescales. This means that all the particles responsible for the emission are able to cool almost immediately on a timescale much smaller compared to the timescale needed for the outflow to expand significantly. On the opposite regime, instead, we have that the losses due to radiative emission are almost negligible. And so in these two cases, we analyzed the two results and what we expect. So in the radiative regime, what is dominating in the observer frame is the emission from the last emitting surface. And so what is giving the spectral evolution is the so-called high latitude emission. What is the latitude emission? The observer at the beginning observes the emission coming from the core of the jet, and for larger times, he receives the photons coming from larger angles, but these photons at the same time are less boosted due to the Doppler factor dependency on the angle theta. So what the effect is that at the same time the flux is dimmer, but also the spectrum is systematically redshifted in the observer frame. The problem is that if we try to model this carefully, we obtain theoretical curves that are systematically shallower than the observed points. So in order to solve this inconsistency, we went to the opposite regime, so the adiabatic regime. And you see that the agreement in this case is much better. So what is the assumption in this case? The assumption is that since we are in an adiabatic regime, there is a conservation of entropy. So you see that if the volume of the outflow is increasing, there is a decrease of the average energy of the particles. And then if we also assume that the spectrum is dominated by synchrotron emission, the peak frequency goes down due to the drop of the average energy of particles. And at the same time, the peak flux of the spectrum is related to the strength of the magnetic field B, for which we use a prescription, which is this one, which depends on the parameter lambda. And you can see that the agreement with data is found for a specific range of values of lambda. So we tried, for this reason, to see what is the expected range of lambda that we can indeed expect. So what the value that gives a best fit with data is a value between 0.2 and 0.8. And we try to see what is the expected value of lambda for two different geometrical configuration of the jet. One is the conical jet, meaning that the transversal dimension, small r, of the jet is proportional to the distance from the center of the jet. In the parabolic jet, instead, this transverse dimension grows more slowly, so as the square root of capital R. And we also computed the evolution of B for two ideal cases. One is the case of equipartition, so this means that the magnetic field follows the evolution of the energy density of particles, which is given by adiabatic cooling. On the other hand, we also analyze the case of magnetic flux conservation. So you can see that in the case of conical jet, which is the most simple scenario we can imagine, the values of lambda are systematically larger than what we observe. Instead, the values of lambda are compatible with what we obtain from observation if we simply assume that the jet is parabolic and not conical. Then another very important remark about our results concerns the problem of cooling timescales. So we saw that adiabatic cooling can explain the spectral softening in the steep decay. And this means that particles are not able to cool. This means that the time scale of adiabatic cooling is a lower limit for the radiative cooling timescales. Now, the adiabatic cooling timescale can be derived from light curve fitting, and let's say is order of magnitude 1 second. The problem is that if we compute the cooling timescale for electrons due to synchrotron losses in a typical gamma ray burst environment, these values are extremely low. So, because we expect very large magnetic field in the environments. So in order to have a cooling time scale compatible with 1 second, one should assume extremely low values of magnetic field. But still, in this case, the inverse Compton cooling would be dominant over a synchrotron. So in order to suppress inverse Compton, we should require very large radii, which in turn give an incompatibility with the variability timescales of prompt emission, which is usually less than 1 second. So this seems to give a self-inconsistency to this scenario, but instead it's this inconsistency can be solved if we simply replace electrons with protons. So if we assume that the synchrotron emission, so the dissipation of energy of the jet, is not dominated by electrons but by protons, what is the advantage? The advantage is that the mass of protons is three orders of magnitude larger than the mass of electrons, and this gives a cooling time scale due to associated to synchrotron losses, which is 8 orders of magnitude more or less larger than the cooling time scale for electrons. And so this is, with this assumption, we are able to resolve this inconsistency, and this is a quite important result for the physics of gamma ray burst. So in conclusion, these are, I summarize what I presented now. So the spectral evolution during the steep decay of prompt light pulses in gamma ray bursts is characterized by a universal relation. But this relation is not compatible with the simple highlighted emission scenario. Instead, we need to also include an intrinsic evolution of the spectrum given by the cooling of particles. And adiabatic cooling is enough to explain this spectral evolution relation. And moreover, our results are in agreement with the previous results about spectral fit of prompt emission pulses, which say that the radiative cooling in gamma ray burst is inefficient. So with this, I conclude, and I thank you very much for the attention.
Thank you, Dr. Samuele. So I'll leave some time here. If anyone have any questions or comments, please go ahead and ask Dr. Samuele.
May I ask to Samuele?
Yes.
Samuele, just a very naive question, but the different angle of the light of view, the angle with respect to the direction of the jet and looking at it, does it influence your conclusions?
Sorry, I lost the last word. So the inclination angle between, sorry?
Between the direction of the jet and how we are looking at it. Does this influence your conclusion, or is it a parameter which does not matter?
I think it's not influencing a lot, especially because these maybe there is a reason in the observations, because these are very bright GRBs. The reason is that in order to make a time-resolved spectral analysis, we need a lot of counts, so the GRBs must be very bright. If they are very bright, it's very likely that they are very on axis. So we are observing them really on axis, more or less very few degrees. So we don't expect that this small inclination angle gives a lot of differences. if instead we focus on less bright GRBs, maybe we are observing a bit of axis, and this can give a different behavior, I think, yes.
Okay, thank you.